The idea behind Euler's method is we want to know how much is the function's value at 1.3, but we've got this differential equation. Suppose that we can't solve it and find an exact solution like y equals e to the x squared over 2 plus x or something like that. But we still need to know how much is the function's value at 1.3. Well, you've got this differential equation, which will always tell you the slope of the tangent line at any given x and y. You have an initial starting point, and then what you do is say, okay, start at 1, 4.482, and if I've got a point, and I can find out by plugging in x and y what the slope is, then what I can do is I can find the equation of the tangent line. I can follow that tangent line just for a little bit, just over to 1.1. Then you plug in 1.1 and say, okay, I've now got a new x and y. Take the new x and y, plug them in over here, and you'll get a new slope. And then you say, oh, well, this path that I was following, actually, it should be a little bit steeper and should be going this direction. And then you follow that path until you get to x is equal to a 1.2. Take the 1.2, plug it in, you've got a new y value. Take the new x and the new y value, substitute them, you'll get a new slope, which will then tell you, oh, actually, you should be following this path. And then you plug in 1.3, and then that will tell you, aha, the actual value you were looking for is this y value right here. Now, of course, underneath all of this, there's actually an e function that is going like this. Since we don't know at this point exactly what that e function is, we use these little line segments to follow it along, and they will give us good estimates for what the original function is. So we start with this original x and y value. So this step is often called the h. So we would have h equals 0 is the beginning. So in other words, I'm starting at that given point of 1. And then I'm going to move over to 1.1 later, etc., until I get to 1.3. So h equals 0 means that we haven't moved over yet. We're still at 1. So at h equals 0, we have the point that when x is a 1, y is a 4.482. Now substitute the 1 for x and the 4.482 for y, and we would have 1 times 4.482 plus another 4.482. So in other words, we've got two of them that are 4.482. So that means that y prime is equal to, so in other words, the slope is equal to 8.964. So then you just use beginning algebra to say if you have a point and a slope, you can find the equation of the line. Y minus the y value is equal to the slope times x minus the x value. So the line is going to be y equals 8.964x, and then this, when you distribute it, it's going to be a negative 8.964. And then add this to both sides. And so our equation would be this, and then minus 4.482. Okay, now we're done with this point at 1. Now we move over to 1.1. So now we call that h. We're moving over by 0.1, which is usually given. So in that case, you have to say, okay, now we're over to the point where x equals 1.1. So if x equals a 1.1, y is equal to, and then just plug that in. So 8.964 times 1.1 minus 4.482 8.964 times a 1.1 minus 4.482, 5.378. So now we've got a new x and y value. Now take these new x and y values, put them in there, and find out what the slope is going to be. So the slope is going to be x times y plus y so just use that 5.378, multiply by 1.1, and then add it to itself. It's now an 11.295. So notice that the slope previously was an 8.9. So at this point, the slope is an 8.9. When you move over to this point, the slope is now an 11.29. So that's what I was trying to demonstrate with this picture right here. So the first line tells you, oh, go off like this. And by the time you plug in 1.1, it says, no, you got to be going steeper. And then the next one says, no, go steeper. Okay, so now we've got an x and a y and a slope. So do the point slope formula again. Y minus the y value equals the slope times x minus the x value. And so our new line segment is going to be 11.295x, and then we need to distribute that with this negative 1.1. So times a negative 1.1, and then this needs to be added to both sides. Add 5.378. So that's going to be negative 7.046. Okay, now I just move over to the next point. So at 1.2, so we're basically just going to follow the line segment, this line segment, until we get to where x is a 1.2. So then that's what's called h equals 0.2. So if we have x is a 1.2, then we'd have y equals 11.295 times that 1.2 minus 7.046. So 11.295 times 1.2 minus 7.046. Our new y value is 6.508. So notice the y values are creeping up from 4.4 to 5.3 to 6.5. So we are going up on this thing, and the slopes are getting bigger and bigger. Okay, next, find the slope again. Take these two, substitute them into that equation right there, and so the slope is going to be x times y and then it's plus y so take that last answer, multiply by 1.2, and then plus itself 14.318. Alright, we're almost done. Do the point slope formula again. So y minus the y value equals slope times x minus the x value. And our last line segment to follow is going to be 14.318 times x and then we need to take that number and multiply by a negative 1.2 and then add this to both sides. So our last line segment is got a b value of 10.673. And then finally, all you have to do is plug in, so move over by one more tenth, and if x is equal to 1.3, y is equal to 14.318 times 1.3 minus 10.673. All right, last one. 14.318 times 1.3 minus 10.673. So y at 1.3 is going to be 7.94. And now the last part is to check. If you go back to number 32, this was the solution that we got. So this is the exact solution. This is the actual y value that we were following along with those little straight lines. And then substitute a 1.3. So you'd have e to the 1.3 squared over 2 plus 1.3. The actual answer is 8.542. And what we got was a 7.94. So it's off by a little more than a half a unit. So that's actually not too bad. If you wanted to be more accurate, of course, you just make this, say, 0.05, and then it would have taken us twice as many steps, but we would have had a more accurate answer.